Okay, we'd like to welcome everyone to the webinar. During this webinar, we'll be touching on a wide range of topics. So if you have any questions, please submit them through the question window. After the webinar, we'll have a brief Q&A session, and we'll try and address as many of the questions as possible. So let's begin.
Hi, welcome to Arunda's webcast, Digital Ships, Connected Vessels and Machine Learning. My name is Marty Cochran and I've got with me here Mark Tibbetts. Do you want to introduce yourself, Mark?
Hi, yeah, I'm Mark Tibbetts. I'm lead data scientist for research and development here at Arunda. My background is in physics research.
Yeah, and I'm Marty Cochran. I lead our engineering team in Europe, and my background is in software development, especially in the renewable energy sector. So today we're just going to talk a little bit about our experiences in maritime industry and this new Industry 4.0 world. We've all seen slides like this before. Today, with more sensors being available, cheaper storage, cheaper compute, we have made our way into new business models. So, for example, pump companies, people that used to sell pump are now selling pumping, and we're moving much more into a potential to do like as a service business models and things. Yep. So what we come across when we're talking to maritime operators and customers of ours is there's three main areas they really need to think about when sort of looking at this new way of working. Let's first of all their solution architecture. So do they have access to the sensors? Do they have any data streaming today? Do they have any historical data? And if not, can they get that connectivity they need today? Then analytics, a lot of people have things like threshold alerts, like high and low alarms, but are they actually listened to? Are they something that people respond to in the correct way today, or can they be improved? Things like KPIs and the role of change analytics within those KPIs, anomaly detection and failure prediction are sort of more, newer sort of technology when it comes to streaming large amounts of data. Now anomaly detection gets much easier, and then business decisions based on this analytics. Is that changing your product? Actually changing how you sell your product? It might even be destroying an old business area that you have to create a new one. And then using these analytics, integrating them into your business process. And these are the three main areas that we really try to focus within the maritime industry. What can't be forgotten though, it's very easy for us now to sit and talk about technical abilities, about machine learning, Industry 4.0, all the buzzwords you love to hear. But this is still something that's, it's a human-centric problem. What we really try to achieve is giving the humans in the middle this ability to make better decisions and using all this technology to get to that point.
So with that in mind, let me just see if I can put that into a slightly clearer context for you with some key examples. So the real thing we're trying to do here is build data products for improved decision making. And if you want to think about some example stakeholders, what we want them to do is we want to take their subject matter understanding, some analytics approach, machine learning or otherwise, and make sure that that's integrated into the data product, improve those decisions through the availability of data-driven insights. So think about a vessel captain. Vessels at sea, there's probably not a significant amount of connectivity, and the captain probably cares most about real-time monitoring of the systems on the vessel. So for that, the data product needs to be integrated into the bridge systems, probably needs to be disconnected from the cloud, so deployed analytics on the edge, and needs to be as close to real time as possible. So decisions and actions can be taken in real time based on the data that the ship is generating. Then consider a control room for a company who has several vessels. There, the analyst in the control room may be interested in interfleet benchmarking. So fuel efficiency. Is the fuel efficiency on one ship significantly better than other vessels in the fleet? And if so, what are the actions being taken and what is the data showing about those actions on that vessel, which means you can improve the fuel efficiency of the other vessels. And for that, the product might be some interactive dashboard in the control room. It's probably not in real time. It's probably as data comes from the ships as they go into port. And this might be daily insights or even weekly insights. And then a completely different stakeholder might be an inspector in the Port Authority. So for them, the analytics and the insights they need around inspection planning. Where do they need to make inspections? Where are the highest risks? And to consume those analytics, they probably need some kind of handheld device as they walk around the port. So that is something that's going to be required on demand. So given those examples, you can get an idea that depending on your focus, you're going to be looking at very, very different data products to improve your decision making for your various stakeholders. And then you have to think about, well, where do you get started? So the plot here is illustrating the fact that there are probably two dimensions that you need to be thinking in. The first is the business value. Clearly, the higher the value, the more important this is going to be for you. So what you need to think about is, if I could produce a perfect insight around the decision and the analytics that I want to influence, what would be the impact and the value, probably cost bottom line, of that decision being made? Then the second axis here is the feasibility. So given that insight, what data do I need? Who makes the decision? What data is available to them? And how can I get those data to make them available for analytics? And that might make something more feasible or less feasible. So as an example of value, in the maritime industry, we hear from most operators that fuel efficiency is the primary focus for vessel performance. For feasibility, then you have to ask, are the data related to that vessel performance captured reliably? And you can also think about feasibility as a risk factor. So things that have low feasibility represent a higher risk of failure. If you're going to put a lot of effort into trying to make a low feasible project feasible, then you're going to take a lot of time. And if it ends up failing, you've invested a lot of resource and you've lost that money. So what we find the best thing to do is to start with the more feasible use cases. And as you address those use cases, you start to learn about the systems that you're modeling, and you start to understand how things that originally seemed quite infeasible to you can become more feasible as you make your journey through your analytics. And then data collection. So to be successful with analytics, context and consistency of your data is everything. If you're collecting data through handwritten noon reports, you're not going to be doing significant amount of advanced analytics at this stage. What you need to focus on is continuous capture of those data rather than just one data point a day, and they need to be digitally captured. So your analytic insights will require some kind of systematically structured, trustworthy data available to run those analytic algorithms on. And it's important that you own as much of those data as possible. If you're relying on third-party data sources, that can add expense and it can increase risk. If the company that you're buying those data from goes out of business, you can no longer run those analytics. So when you're thinking about AIS or speed and direction information, these are data sources which you can buy third-party, but really you should be recording it yourself because you don't want to rely on those third-party sources. And the key thing to keep in mind is that your maritime assets were not built with real-time digital analytics in mind. Now, Marty will go into giving some of the context about why that's the case and what you can do to overcome some of those challenges.
Yeah, so exactly what we've just said is all well and good sort of theoretically. So really what I want to do is spend a bit of time on what we in Arundo have found when trying to actually do this in the real world. Here's a list of 7 things that I find are the key technical problems that we've seen. Number 1 is right at the core, actually connecting to these control systems. If you have a ship, yes, it might be from the 80s, it probably has a control system on it, but can you actually connect to it? And then number 2, well, maybe you can get connected to it, maybe have some details about it, but do you actually know what data is available and what frequency that data is available at? Then the next sort of 3 big pain points are all based around connectivity. So it might be that you are connected very regularly, but it's very poor. So you need the ability to sort of have offline storage or buffer that data. So if you're trying to stream this data to some cloud service and you're going in and out of connectivity, that's a real problem. So being able to actually store that offline, and then when you're reconnected, pushing that onto your cloud service. Or maybe just low bandwidth means that you can't actually collect the frequency of data you want to. Maybe you want to collect data at one time a second, but your bandwidth is just so low that you can't actually send that amount of data. Or in a lot of cases, we have like once a shift satellite connection. So, an operator has satellite connections in all their assets, but it's maybe only switched on to do one batch upload and one batch download once every shift, for example. This can be very expensive, so obviously it's not done that much, and to limit that the megabytes sent or the gigabytes sent back and forward is very important. Then the next thing is actually if you have models running, right? If you have actually successfully developed a model that runs very well and is proven to be very valuable, well, what happens if you're offline? What happens if you can't get connected to, say, a cloud service that you have this model running on, and how that will affect your operations? And then pretty much the most important thing in everything we touch is security. The last thing you want is your assets to be connected, but also opening up a large possible security threat to your assets. So let's just start by the simple one, control systems. Most of these control systems, rarely we find that they have a very specific or a unique type of control system. Most of them stick to some kind of standard. The main four that we find are down the left-hand side. So we've got OPC, both UA and DA, Modbus serial, and say TCP, maybe even RTU sometimes, and then CAN bus, which is a newer sort of engine control system. So getting connection to them is important. Typically, if they expose these sort of standard interfaces, then we can get connected to them, and most people will be able to connect to that. The next thing then really is how do you explore what they give or what's available in those control systems. In Arundo, as part of our Edge agent, we did develop this auto tag browsing, which has been really helpful for this. We did come across quite a lot of customers that knew about say, for example, an OPC connection they could get access to, but they didn't actually know what tags were available. So within our Edge agent, the thing that we use for actually connecting to control systems and streaming the data, we built this Modbus and OPC browsing functionality, where we actually connect to the control system and we'll display to the user all the tags that we can find that are available, which really just helps give you the overview of what's possible. Then we talked a bit about offline storage and internet connectivity. This is another thing that we explicitly have tried to solve. A lot of cases out there, it's very easy to get a connection to a control system, choose a tag or two, and then stream the data live to some cloud platform. But actually then how you store that data offline, determine when you're online and offline, that's, it sounds a very easy thing to do, but it's actually, there's a lot of nuances in there and things that isn't quite as easy as just saying, oh, I'm online, okay, just throw all the data that I've been buffering for the last 7 days up there. How you compress that data and make the most use out of that internet connection you have is very important. So you'll see with our Edge agent, we give options when you're installing it, how long you want to store unsent tags, for example, to have some sort of buffer there. It's very easy if you know you're only ever offline for example, 1 day, you can reduce it, or if you're offline for 14 days, then you can add that. Then we got to the point that I had around actually not being able to stream all the data you have. And this is really important. We say that whatever data you have, or what you'll hear a lot of people say is you don't know what you don't know until you don't know. And that's very important, right? When you have a huge amount of data and you want to stream it, but you can't, how do you actually handle that? What we've done with our Edge agent in Arundo is we have given the ability to actually deploy models down to the edge. So if you've developed some model that needs a high frequency of data and a lot of different tags that you don't actually want to send across the wire because of, for example, expensive satellite connections, you can deploy that model down to the edge, stream all that sort of high frequency data into that model, and maybe only stream the output and some maybe some of the tags that you might want to store later on in a cloud environment. This is very powerful, meaning that even with very poor bandwidth or very limited connectivity, you can still run your analytics on the edge and just stream the insights to the cloud platform. Then we get into the case of what I mentioned as well around how do you access these models offline. it's very important that your edge application, or the thing that you've actually got running down in a disconnected state, can also, if you have something like an anomaly detect model running, can actually help the people on the local network see that. So with our edge agent as well, we put that as a high focus, that if we're running a model offline, then it's very important that people can actually see the output of that model offline. So this is just an example of one of our models running on the edge agent that anyone on the local area network can actually access and browse in a web browser, which will let you see actually how the anomaly detect algorithm is running. Then we're on to the big one, security. I've put just 4 points here, which is really the 4 main points we come across. It doesn't mean this is the full A to Z list, but it's ones that hopefully are interesting to hear about for you. But it's certainly the 4 big topics we address. Number 1, which really should be the easiest, which is actually physical security. So if you're putting a piece of hardware on a ship, well, is there any way you can just physically secure that? Should it be behind a locked door? Should it be somewhere that people can't access it, or is it perfectly fine that the people on your ship could have access to this box? Things like logging in as well. If it's running on something like a Windows PC, is it something that should be part of a domain, like a central company domain? Should it be behind like an Azure Pass secure vault or anything like that? You know, or is it okay that anyone who in theory has access to the physical box can just connect the screen and view all the edge agent data? Number 2 then is the control system security. Even if you're putting an edge device down at the edge that's connecting to a control system, how can you as an asset owner actually ensure that edge box never gets a chance to rewrite something back onto your control system? And there's lots of ways to do this. We have different ways that we've worked with our customers for putting in things like a special firewall that only lets data to flow one way, for example. So if you open up a certain port in a firewall, you can ensure that the data only flows from control system to edge. And even if the edge box tries to push something back, it won't be allowed to the firewall. Also, things like OPC UA, it's very easy to add its own security rules. So you could say, okay, well, on this IP address and this port, I'm actually going to only ever allow to read access. So again, even if for some reason the edge software that you're using does start to try and write back to the control system, either intentionally or unintentionally, you can have control of that through your control system security itself. Then data transport security. So the last thing you want to do is have all your data from your assets streaming across the wire and giving people the opportunity out there to access that. So there's various different encryption techniques that are widely used today that can be followed. You can even do things like intrusion prevention analytics. So not just doing analytics on your assets, but actually doing analytics on the edge devices themselves. So really trying to detect any anomalies in the data to sort of see if maybe someone has somehow managed to get through your encryption techniques. Things even like user access logging, logging in or monitoring to see if everyone who should be accessing the edge box really is, or if there's weird patterns, someone may be accessing it at 2 a.m. every day. That might be totally normal in your case, that might be on a shift change or something, but really just logging that user access. And then you can go to more advanced ways, like actually adding your own virtual VPN and things as well, from edge to cloud, just to really give another level of security. Now, with most edge devices out there today, they give some sort of remote management capability. So that's things like updating devices remotely. So if you have a full fleet of ships, for example, and you want to be able to remotely manage them from a central area, you want to be able to make sure that's done securely. It's very important that you're not opening the control systems to remote attacks. So once you open up a gate to do things like updating remotely, then you're potentially opening up an area to let someone do a remote attack as well. So how you secure that? And again, similar things to above, doing things like user access logging, intrusion prevention analytics and things is very important in there.
Okay, so now we have a clearer picture of data capture. The question becomes, what types of analytics can you use those data for? And depending on where you are, the different use cases that you'll come across will be completely varied. So if you're at the ports, you may be thinking about things like logistic optimization. If you're doing scheduling and navigation, route optimization, fleet management, AIS messaging. Operations, there's vessel performance, predictive maintenance, crew management, maintenance itself, there's condition-based maintenance, propulsion and machinery health, and we'll dig into some of these cases in a bit more detail in the following slides. So a couple of specific use cases. First of all, route optimization. So you can just follow the grand circle route from port to port. But in principle, if you know in advance about external factors such as weather, sea conditions, those kind of things, you can build optimization models which actually determine the most efficient route to port to take, which isn't necessarily following the grand circle. As long as you include the correct boundary conditions such as shipping lanes, any other specific requirements about time to get to port, all of those kind of things, you can then build an application which allows you to forecast and follow the best route as you transverse the ocean. And then what we see a lot in performance forecasting is this classic speed-power relationship. So as a vessel travels along, its performance will degrade due to effects like underwater fouling. This means that the amount of power that you have to put in to get a certain speed will increase. And that is obviously going to burn more fuel. So what we want to do is you want to be able to use historical data to understand what is the rate of that degradation in the performance of the vessel. Can I forecast when the right time to do a fouling cleaning is? But that needs the context that we referred to earlier. And so just to build on that a bit more, the context comes from event data. So when you're building models on historical data, you need to know what happened in the historical data and when it happened. And those are the labels which you use to derive the analytical models. So in the context of hull fouling, there may be a number of different labels that you want to think about. When did that cleaning start and finish? Were you in the dry dock or did you put divers down? Was it just a cleaning of the propeller or was the full hull cleaned? And the reason that these different factors are important are kind of illustrated with the schematic on the right, because the different types of interventions will have different changes in the relative performances. So for example, divers cleaning propeller without a full hull cleaning will lead to a marginal increase in performance. But if you're going to do a full dry dock cleaning, you're going to get a much larger increase in performance, however, at a larger cost because it takes more time and the vessel's out of operation for longer. And so all of these factors need to be balanced when training the model, which is doing your forecasting and suggesting to you the best way to operate your cleaning regimes. And then a critical point in being successful in analytics in any kind of industry is not to isolate your data science from your expert knowledge. So I, as a data scientist, have a good understanding of machine learning methods that might be able to algorithmically learn some unknown function relating the available input, such as sensor data, to a desired output, such as fuel efficiency. However, I don't necessarily have the intimate knowledge of the systems that those sensors are coming from. And so in isolation, I may not engineer the best features for my model to make the most powerful predictions. And what that needs is learning directly with a significant amount of labeled and well-structured data. And that may in practice not exist. So how do I get that information? Well, I have to sit down with the system specialist and I have to work with them to understand the physical systems. I have to understand how the sensor data can be engineered into things that make sense for the variable that I'm trying to predict. And if I don't sit down with that system specialist, then that information is not captured. Expert knowledge needs to be integrated into a learned system. And you're going to be significantly more successful in building analytics if you bridge that gap between the data scientist and the system experts. And then think about the methods. So we've described that, if you're going from a case where you're not connected, you only have noon reports, and then you may have these high, high, low, low alarms that Marty referred to in your systems. Now, as you collect more data, you might then be able to build KPIs, process signals into each other. These models on the edge, they might be able to calculate these KPIs in real time, and you might be able to build a data product which allows you to explore the history of those KPIs. But these are still rules-based methods. So where does the machine learning come in? Well, this is in being able to identify, classify, and predict potential failures. So anomaly detection. What do I need to apply anomaly detection? Well, I need a lot of data of normal operation, because anomaly detection is about comparing normal operation to how things are operating now. And if things are operating now do not look like how they looked when things were operating normally, last week, last month, then I need to raise an alarm. And I need to build a data product which allows the user to investigate the sources of data which go into that algorithm and understand why those data have drifted from the normal operation. Now, that's all well and good, but that's putting a lot of responsibility on the user to then dig into the system and find out what's wrong. What we'd rather do is we'd rather have the algorithm itself classify the failure. But what's needed for that? Well, for that, I need to have seen a lot of examples of that failure in the historical data, because I need to be able to, in a statistically robust way, train an algorithm to recognize what that failure looks like in the data versus what the normal operation looks like. And if I have enough examples of several different failure classes, then I might be able to classify one type of failure from another. But that, again, is not really predictive maintenance. And that's obviously the holy grail that we try and achieve in these types of analytics journeys. So what do you need for predictive maintenance? Well, you don't just need the examples of the failures in your historical data. You need to see the full path from normal operation through to the failure, because there will be a pattern, a drift in several sensor variables, for example, which are going to give you advanced warning that a failure is coming. And it may be that those drifts are very, very subtle. And the more subtle those drifts are, the more examples of those paths to failure that you need. Now, fortunately, in heavy systems equipment that you might find on a vessel, failures tend to be quite rare. That's good for operations, but it's bad for analytics. Because if I don't have a lot of those examples, it's going to be a huge challenge to get to this path to failure data that I need to build these models. A solution to that is to think about, well, what data can I leverage across the fleet? Okay, failures might be rare on one vessel, but if I have access to data from tens of vessels or hundreds of vessels, then I get more and more examples of those failures. So I can do a better job of predicting those failures algorithmically. And then the final thing to think about is, what can I do with the techniques which are being developed by Google, Facebook, and others around deep learning? So these are the computer vision systems, or the natural language processing systems, or the audio recognition systems. Are there ways that I can reimagine my use case? Would I be able to put a video on a vessel, or take photos of a piece of equipment, and would I be able to recognize from photos whether there's corrosion or anything like that? If I can do that, if I can have an expert point to photos and tell me that is a corrosion, that is not a corrosion, then I can take these methods, these deep learning computer vision methods that are available from the likes of Google, and I can apply that method in a technique called transfer learning, which allows me to re-optimize the algorithm that I've taken from Google to learn the specifics of the problem which I'm looking at. And so if you can reimagine your use case with images, audio, or video, then you can think about applying these deep learning techniques and really taking advantage of these very, very high performing algorithms. Of course, once you've trained your model, you need to put it in operation. In that data product, you need to make those insights available to the user. However, it's not going to be perfect out of the box. And that means you have to take user feedback seriously, and you have to update both the product and the algorithm accordingly. The most significant barrier to advanced analytics in operation is user trust. If I'm on a vessel and I suddenly see a new dashboard, which is this black box machine learning model, how do I know to trust the output of that model? I probably have a preference for transparent insights over those kind of black box decisions. And the real problem there is these models provide fuzzy logic. We're living in a world of statistics and probabilities. That means we're not going to be right every time. False alarms can and will occur. So therefore, we need to define very clear policies on how a user should manage them, understand how frequently they are expected to occur, and make sure we understand what is the cost of taking an action on a false alarm versus not taking an action on a real alarm. And is there a balance to be struck between the two? And what we mean by that is, you can use these statistical metrics such as accuracy and precision and recall and so on, but those don't mean much to an operator. What an operator needs to know is, if I take this action and it turns out to be a false alarm, how much more is that going to cost me? And if I don't take the action and it turns out to be a real alarm, how much is that going to cost me? And how do those two balance against each other? So how can I make the best informed decision possible? And then model performance. You're training it on a snapshot of historical data. It becomes a fingerprint to those historical data. However, we're dealing with systems that change as a function of time. And so that model performance, if I just leave it with data from 2 years ago, 3 years ago, will degrade over time. And as I continuously collect operator feedback, I can monitor how that's degrading. And then I can even go in and retrain with more recent data when required. The most important thing is that if the fuzzy logic that we described above, the relative amount of false and true alarms, is changing in favor of more false alarms, then clearly we need to go in and understand from more recent data why that is, and update the system with a retraining to make sure that we can capture and deploy a new version of the model which takes that into account. So take the user feedback seriously, and the system is dynamic once it's deployed. Sources of data can also be lost. So how robust is your model to losing a set of sensor signals? Or as we said earlier, do you rely on third-party data? Is that no longer available? You really have to keep that in mind when building these systems. So our key lessons from this webinar. Consider solution architecture, data analytics, and operational implications together. They're all pieces of a whole, and the whole is much larger than the sum of the parts. Find low-risk ways to get started. Don't wait for the perfect sensor or instrument. Don't concentrate on the high-risk things which will take years to deliver and still going to end up in failure. Start with the low-hanging fruit, go on an analytics journey, and then have your roadmap which takes you to the high-value insights. And of course, if you have low-hanging fruit of high value, start there. Focus on that business value. What are you going to change to reduce your costs or increase your revenue? Have a business mindset when you're defining what are your analytic approaches to take, and then create data products for your people. We're talking about human in the loop artificial intelligence. You're not building models for the data, you're building products for people to make better decisions in light of insights that are generated from models on those data.
So then that's just been our quick, 20 minutes insight into some of the things that we come across on a daily basis, and what we really want to think is the most important things to share with you. But now we're going to a bit of a Q&A session, and you're welcome to ask whatever questions that you have after you've seen the slides that we've just shown. Thanks.
Okay, I think we have a few questions that maybe our organizers would like to answer.
Sure. Where do you want to start, Marty?
Yeah, well, we can start, I guess, right at the top. We have a question here coming in: the key differentiators between conventional way of plant performance monitoring and with IoT for particular marine plant, e.g., boiler and main engine. I guess you're the best person to talk about this, Mark, when it comes to sort of manufacturing maintenance schedules versus data-driven schedules.
Yeah, sure. So, I mean, if you take a piece of equipment like a boiler or a generator or something like that, there's going to be a manufacturer specification of every X number of hours you should go in and do a full maintenance of that piece of equipment. What the IoT solution and what monitoring sensors and applying analytics allows you to do is provide further context around that piece of equipment, understand how it compares to, say, other similar pieces of equipment, and you can make determinations as can I actually run this thing for longer before I do the maintenance, those kind of things. So this is more into kind of prescriptive and predictive maintenance rather than kind of schedule-based maintenance, and that's one of the real advantages you can get out of IoT solutions and applying analytics to those types of data.
Yeah, the question after that was along very similar lines: is can IoT solution be applicable for ship energy optimization, like two-stroke propulsion engine, and so on? And it's yes, you can obviously do a lot of optimization when it comes to, say, fuel and different types of fouling and stuff that we've looked at with correspondence to fuel optimization. But along the same thing is what Mark just talked about, actually, around maintenance. Again, down the same line of not having to always follow the exact manufacturer specification, being able to drive your maintenance based on data. That's the main benefit of doing this, taking this kind of approach to optimizing two-stroke engines, etc.
Yeah, and I think there's a kind of more general point here that you're able to kind of take the bigger picture into account. So whereas, say, in the old operating procedures, you may have had your crew collating noon reports once a day and collecting the important sources of data once a day. What you're doing now in this new regime is you're continuously capturing data across your fleet of vessels. And this means that in real time, or as close to real time as possible, given bandwidth connections of satellites when you're at sea and so on, you can cross benchmark your fleet against each other. You can see where are the ships that are performing well, where are the ships that are not performing so well. Is that for reasons of crew? Is that for reasons of equipment? And you can get these insights fast and in close to real time, or at least as fast as you can get the data and cross-reference them against each other. Whereas previously, if you had handwritten reports, you would have to kind of take those on shore, collate them, have people manually going through them and doing these comparisons. It's much more labor-intensive effort. So the digital world that we're talking about here is about getting to solutions and analytic insights of value faster.
Yeah, then there's also a few questions around: will we be sending out the slides and stuff after? Absolutely. This webcast is being recorded, and we will be sharing it on, for example, like LinkedIn and things afterwards. There's some other questions around also, like what we as a company, Arundo, do, and do we provide consultancy, etc., for especially to Maritime. For that, I suggest speaking directly to our sales team. You're more than welcome to contact them just through our website and things. They would be the best people to really go into detail on how we deliver some of this work to our customers today. Let's see, we have another question that says, thanks for the great webinar, gentlemen. That's awesome. Thank you. That's the easiest question I've ever had.
Yeah, and just to sort of say a little bit around what it is Arundo do. I mean, we're not just about kind of doing these analytics for the sake of consultancy. We really think the value here is in building software products and data products which allow the output of those analytics to be consumed by the users. And we kind of stressed this a few times in the webinar. If you want to be successful here, you have to think about who is going to be consuming these analytics, how are their decisions going to be influenced by the data, how are they going to change, and what are the products they need to have in hand. So we don't just sort of do consultancy around what are the right analytics to apply to a given use case. We're building software products and providing tools to allow others to build software products if they have their own analytics teams to implement these solutions and make them available.
Yeah, for sure. We didn't want the slides to sound like just a sales pitch from Arundo, but we are a software company that really designs software to fix a lot of these challenges we find in various different verticals within the heavy asset industry. Let's see what else we've got here. We're just reading down them.
I guess there's one here. So it's about measuring improvement before and after IoT implementation. Like, you know, can you do this quantitatively and qualitatively? Well, quantitatively, there are sort of some things that perhaps you were monitoring beforehand. I mean, really, this is kind of going to be a phased approach as we described with the analytics. So as you're kind of moving through your journey from kind of KPIs without having historical data through to anomaly detection, through to classification, you know, you can quantitatively measure, like, you know, are these analytic insights correct? Are they matching up with what I'm actually seeing on the ground? And you can monitor that. And as we commented in the webinar, perform, you know, appropriate retrainings, automating that process if necessary to keep the analytics fresh and relevant. And then from, you know, the qualitative perspective, I mean, you're going to be changing the way you operate, and your staff and your crews are going to be changing the way they operate. So you're going to be learning to really kind of work with these new technology to make better decisions and to ultimately be a more efficient and effective company and save your bottom line.
Yep. So from looking down them, I think we've covered most of them here. There was a few along the same topic. Maybe, you know, we have a few more minutes if there's any final questions anybody wants to submit before we close out. Obviously, you're more than welcome to contact us at any point afterwards. You know, if there's some follow-up questions or more sort of technical deep dives or something you wanted to go into.
So if anyone has any final questions, you can just type them right into the question box on your screen. Okay, I don't see any more coming in. Just want to thank you guys for taking the time to do the webinar today.
Thank you, Mark, for hosting. It's a pleasure.
Thanks for everyone for attending. This was it was really nice to talk to you.
Thank you, everyone.